Welcome back. Let's discuss the operating principle of the crystalline silicon solar cell. In this video I will discuss several technical aspects which play an important role in the generation and collection of light-excited charge carriers and the reduction of optical losses in crystalline silicon solar cells. The first learning objective is to understand all design rules related to the reduction of charge carrier recombination losses. We will discuss how surface passivation of cells, reduction of contact area, selective highly doped emitters, back surface field and the metal contact grid plays a role in this design rule. The second learning objective is to understand all design rules related to the reduction of optical losses. We will discuss how shading contacts, anti-reflection coating, texturing surface and interfaces, parasitic absorption by non-active photovoltaic layers and back reflectors play a role in this design rule. Let's look at the solar cell. In part 1 of the solar energy MOOC, we have discussed how an illuminated PN junction can operate as a solar cell. In this illustration we have in these video lectures both the p-doped and n-doped region at the same thickness. If you look at the crystalline silicon technology, this is not the case in real devices. Let's look at the most conventional crystalline silicon solar cell based on the so-called back surface field architecture. The solar cell is based on a p-type silicon wafer. The N layer in this illustration, colored beige orange, is the n-doped layer in the crystalline silicon PV technology. This layer is often called the emitter layer. This n-type emitter layer is much thinner than the wafer. The emitter has a thickness in the order of 1 micron. The rest p-doped wafer can be in the order of 100 up to even 300 microns. As discussed in part 1 of this solar energy MOOC, a large fraction of the light is absorbed close to the front surface of the solar cell. This is the generation profile as we have discussed earlier. You see that in the first 10 microns most charge carriers are excited. By making the front emitter layer very thin, a large fraction of the light-excited charge carriers generated by the incoming light are created within the diffusion length of the p-n junction. One of the processing methods to make the emitter layer is by solid-state diffusion. The wafers are placed in a furnace where the dopant atoms are present in the atmosphere in the form of phosphine. These atoms react at these high temperatures with the surface. At these high temperatures, the dopant atoms are mobile in the solid and based on Fick's law, the dopant atoms will diffuse into the wafer. Similar as we have discussed in part 1 of this MOOC for charge carrier diffusion, net diffusion occurs when there is a density gradient. The fusion process is controlled such that the dopants penetrate into the solid to establish the desired emitter thickness. Now we are going to look at how the light-excited charge carriers in the crystalline silicon solar cells are collected. We will discuss the crucial issues which play an important role in this charge collection. This excludes the emitter layer, the metal contacts and the back contact. First, last week we have discussed the importance of the high lifetimes of charge carriers. High lifetimes guarantee large open circuit voltages, or in other words, the best utilization of the bandgap energy. This means that we have to reduce the recombination losses as much as possible. In addition, recombination limits the collected current as well. Recombination in silicon occurs, as discussed earlier, through the Shockley-Rithold recombination and Auger recombination. Let's consider the Shockley-Rithold recombination. This can occur at defects of impurities in the bulk of the p-type wafer. Or this can occur at defects or impurities at the surface of the wafer. Or Shockley-Rithold recombination can occur at the defect-rich interface between the metals and the silicon. Keep these loss mechanisms in mind as it will determine the solar cell design choices. Let's start with the emitter layer. At the p-n junction, the light-excited minority charge carriers are separated at the p-n junction. The minority electrons in the p layer drift to the n layer. These electrons have to be collected. Since the silicon N emitter is not conductive enough, we have to use the more conductive metal contacts. The metal contacts are placed on top of the emitter layer. Here the metal contacts are made of the cheap metal aluminium. This means that the electrons have to diffuse laterally through the emitter layer to the contact to be collected. Let's see what the challenges for this transport of electrons to the contacts are. First, the bare crystalline silicon surface contains many defects. The surface silicon atoms have some valence electrons which cannot make a molecular orbital with the absent neighboring atoms, here indicated with the red lines. These valence orbitals containing only one electron at the surface act like defects, also called dangling bonds. At these defects, the charge carriers can recombine through the earlier mentioned Shockley-Reed-Hall process. The probability and the speed at which charge carriers can recombine is usually expressed in the terms of the surface recombination velocity. Since a large fraction of the charge carriers are generated close to the front surface, a high surface recombination velocity at the emitter front surface will lead to charge carriers losses and consequently lower short circuit current densities. The lifetime of these charge carriers is limited by the recombination process at the wafer surface. In order to reduce the surface recombination, two approaches are used. The first is based on reducing the number of defects at the surface. This can be achieved by the deposition of a thin layer of different material on top of the surface. This material partially restores the bonding environment of the silicon atom. In addition, the material must be an insulator. It must force the electrons to remain in and move through the emitter layer. Typical chemical passivation layers being used on emitter layers are silicon oxide and silicon nitride. Silicon oxide layers are formed by heating up the silicon surface in an oxygen-rich atmosphere. The surface oxidizes, resulting in a thin layer of silicon oxide. Silicon nitride can be deposited using plasma-enhanced chemical vapor deposition. We will come back to that process technology when we talk about thin film PV technologies. A second approach to reduce the surface recombination velocity is to reduce the minority charge carrier density near the surface. As the surface recombination velocity is limited by the minority charge carriers, a low as possible minority charge carrier density at the surface region would be beneficial. It means that with increasing the doping of the emitter layer, we decrease the density of the minority charge carriers. This results in a lower recombination velocity at the surface. However, this is again in competition with the diffusion length of the minority charge carriers. In this case, the hole indicated by the white circle with a plus sign. Note that many charge carriers are generated by the bluish photon close to the surface. To utilize these light-excited minority charge carriers, the diffusion length of the holes has to be large enough to reach the depletion zone at the p-n junction, as indicated by the blue arrow. Increasing doping levels decrease the diffusion length of the minority holes in the emitter layer. The fusion length can become so small that the minority charge carriers are unable to reach the p-n junction. Therefore, too high doping levels or too thick emitter layers would result in a poor blue response, or in other words, a low external quantum efficiency values in the blue part of the solar spectrum. Such layer could be referred to as a dead layer, as the light-excited minority charge carriers cannot be collected. Now we look in more detail to the metal-emitter interface. A problem at this metal-emitter interface is that we cannot use an insulating passivation layer like silicon oxide or silicon nitride anymore, as we need electrons to conduct from the semiconductor material to the metal. This means that the metal semiconductor interface has more defects and therefore an unwelcome high interface recombination velocity. In addition, a metal semiconductor material induces a barrier for the majority charge carriers. In view of the scope of this course, it is too much detail to discuss this barrier in great detail. Keep in mind that this barrier will give rise to a higher contact resistance. Again, high doping levels can reduce the recombination velocity at the metal semiconductor interface and reduce the contact resistance. As a consequence, it is preferred to reduce the area of the interface between the metal and the semiconductor to minimize the recombination at the interface defects as much as possible, and to have the emitter directly under the contact as heavily doped as possible. This higher doped region is indicated here by N++. In the figure you see that the contact area between metal and the interface is kept as small as possible. The sides of the metal contacts are buried in the insulating passivation layer. The area below the contact has been heavily doped. These two approaches reduce the recombination and collection losses at the metal contact. At the back surface of the solar cell, we have a similar issue playing a role. As the electrons have to be collected in the N layer, the holes are collected at the back contact. As electrons are the only charge carriers that exist in the metal, you have to realize that the holes recombine with the electrons at the contact interface. If the distance between the PN interface and the back contact is smaller than the typical diffusion length of the minority electrons, the latter mentioned minority electrons can be lost at the defects at the back contact interface due to Shockley-Reed hole recombination. How can we reduce this loss mechanism? First, we can reduce again the area between the metal contact and the semiconductor. We can make point contacts. The rest of the rear surface is then passivated by an insulating passivation layer, similar as we have discussed for the cases of the emitter front surface. The loss mechanism of recombination of electrons at the back contact can be further reduced by a so-called back surface field. A higher p-doped region is placed above the point contacts at the rear surface indicated by P++. How does the back surface field work? For the moment we have put the back contact structure on its side. Next to the contact you see the bent diagram indicating the various interfaces. The interface between the lower dope P region and the higher dope P++ region acts like a PN junction. In this case, it will act as a barrier for the light-excited minority electrons in the lower doped region to diffuse to the back surface. The space charge field behaves like a passivation of the defects at the back contact interface and allows to have higher levels for the electron minority density in the p-doped bulk. In the next video we will continue our discussion on the design rules of the crystalline silicon solar cell. We will discuss metal contact grid and the design rules for reduction of optical losses. The electrons are collected at the contacts. So let's look how the contact grid looks like. See you in the next video.